Hello and welcome to the second GCSE Geography video tutorial revision session. This one covers Paper 1, Topic 1, which is the changing landscapes of the UK. It is by far the largest section, so please bear with and have regular breaks if required. So a bit of advice and disclaimers about the video. Not all of the images used are my own. I get no profit from any video tutorial. Feel free to pause and make notes at your own pace. It's one take, so please ignore any poor delivery or stumbling that happens. Please tell other GCSE geographers if you found this session or any other sessions I've made useful at all. And if you have any requests for any video tutorials you'd like to see, then I will more than happily try and accommodate those requests. There are 13 in total and I've tried to cover all bases, but you never know. So section A, which is the entire topic, has 3 questions in it in total. The first question, which is worth just 6 marks, is generally quite large in terms of the amount of content that's included, but there's low weighting of questions. There are only 1 marker questions or just a 2-mark question as well. So what I can almost guarantee is there will be a question about UK rock types specifically. If you look at the map on the right hand side, this shows you the main different types of igneous, metamorphic and sedimentary rock and where you would find them in the UK. Now there was a question in a GCSE paper recently where they just had a blank map of the UK and the igneous rock highlighted but without the label, and you needed to know that that was the igneous rock. So please just know that by heart. What you also need to be aware of, though, is not just the type of rock, igneous, sedimentary, metamorphic, but also examples of those rocks: granite and basalt for igneous, chalk, sandstone, limestone, mudstone, sedimentary, and slate or schist for metamorphic rock. But more importantly than that, really, is you need to know characteristics and the formation of the different types of rock. So the characteristics of igneous rock is that it is very hard and resistant, has visible crystals, and is mostly impermeable. Sedimentary rock is formed in layers, can contain fossils. I wouldn't say something like it's not resistant, because there is some very resistant sedimentary rocks, such as the millstone grit. So don't fall into that trap. Metamorphic rock, again, generally hard and resistant, and mostly they're made of sedimentary rock that's been heated and changed. Hence why they're called metamorphic, because they've metamorphosed. The formation, again, you could just summarise up in a sentence really, but igneous rocks are formed from molten magma from the Earth's mantle or volcanic activity. Sedimentary rock is formed from, unsurprisingly, sediments from rivers or from the skeletons of coral reefs or fish that are layered on the seabed and eventually get compacted and cemented together. And metamorphic rock are just when sedimentary rocks have been heated and put under great pressure in the Earth's mantle. So the next part you'd need to know about this particular 6-mark section is uplands and lowlands of the UK. And this dotted line here, called the Tees Exe line, named after the River Tees and the River Exe, generally divides up the UK into its upland and its lowland areas. So upland UK is found in the north and west and contains most of the mountain areas. The geology is largely hard igneous metamorphic rock, or the harder sedimentary rocks, like I mentioned the millstone grit earlier. So that makes them harder to erode and therefore remain as high upland, whilst the softer rock around them erodes downwards. Also, historic plate boundary processes, so tectonic processes 520 million years ago, mean that 2 plates were pushed and smushed together to create fold mountains. And that created the mountains of Scotland, Wales and the Lake District in these areas. So that's where we get our main mountainous regions. Around 50 to 60 million years ago, much more recently, plates moved also apart to let magma spill onto the surface, and that occurred up here, very particularly in the Giant's Causeway area of Northern Ireland. And so those basalt igneous rocks are formed there and over here on the sort of west coast of Scotland too. Now, lowland UK, which is largely the sort of south and east areas of the UK, are made of softer sedimentary rocks, so they're much easier to erode, and that generally makes the land a flatter profile. So one notable example is the Weald in between the South and North Downs of Sussex, which we've looked at and we did a cross-section of back in the day, quite a while ago now. Now, you may get OS map questions around about looking at past physical processes, and the past physical processes involve tectonics, glacial processes and river processes, and they're all naturally occurring things that have formed the landscape we see today. So the first thing I would note, pointing out with all these arrows you can see they're about to be filled in, is that this is a very high area of land, and that's because of all these little lines, they're called contour lines, and a contour line represents a change in height. So when these contour lines are crammed together, there's a lot of change in height, i.e. a mountain. So things that you can spot on OS maps to help tell you that there's a certain type of climate or physical process going on are the words such as crags. Now crags just means an exposed rocky rock face, so something that has got lots of joints and maybe freeze-thaw weatherings happening in there. And there's a couple of places called crags. You've got tarn crags up there as well. So crags tend to be areas where there's it's high above sea level and it's very, very cold, so lots of freeze-thaw weathering. And you can see the symbol here of these kind of craggy landscape sort of running at the ridge along a mountain. Down here you've got quite a bit of a clue about a river, which is a misfit river. Now what that means is it's a very narrow river relative to the flat wide valley that it sits in. If you look at this red line here, that represents how wide the valley is. Now that valley is wide because it's a U-shaped valley carved out by a glacier back in the old day of the past ice age. So that glacier ran all the way down here, okay, and as a result it carved out this U-shaped valley, and then this river's left behind doesn't really fit in it. It's like me wearing a pair of size XXL trousers. I'm sort of moving around in there, very loose and baggy. Along the top you've also got other features like Scales Tarn, which is an upland lake which is left behind after a glacier rubbed and created a bowl shape, which is filled in with water now. And down here as well you've also got these other rivers that you can see running down, which tells you that the climate is very, very wet in this area too. So there's loads of physical processes on display in this particular map, which show it's a kind of a natural area. We're also interested, however, in human activity on UK landscapes, because those natural activities that you see here, they happened well before we even arrived on land. But as soon as we did arrive, we started to change the landscape ourselves, and we did it a number of ways. So one of the ways was through forestry, and what you've got here is a really good example of where you can see forestry on OS maps. It either says plantation, which tells you it's been planted, or it's got these conifer Christmas trees. Now those are often used for plantations because they are fast growing and you can pack them together because their branches don't stretch out very wide. Now this area is also an area that demonstrates a type of agriculture, what we'd call pastoral agriculture. That means it's got animals in it. And the reason they've used pastoral agriculture, not crops here, is because, again, there's lots of contour lines, which tells you it's steep. Tractors, as resilient as they are not great at going through woods and going up steep slopes, but sheep have no problem doing that whatsoever. That's directly contrasting to this area here. Now this is in Norfolk, this is close to where I grew up, and what you can see here is this flat area, very few contour lines if any. There's a few just this side of the river Waveney, in a place called Alderby, and what we've also done is we've changed the landscape by draining it. So this floodplain land has got lots of ditches and dikes drained, which is perfect for growing crops. It's called grazing marshland, and it's also good for growing things like barley, wheat and rye. It's very flat and it's very good for arable agriculture. So there you go, agriculture is another way we've changed areas of landscape through hill farming, and also through mainly arable farming, which is very, very wide, flat, visible areas, particularly in Norfolk and the southeast. So settlement, and I'm going to use Norwich to demonstrate that, is another very clear example of how we've changed UK landscapes. So what you can see is you've actually got agriculture going on here as well. We know that Norwich is in Norfolk, and these characteristic kind of fields are sectioned off by hedgerows, which you can see as these darker green lines. Norwich grew up around the River Wensum, which you can see flows all the way through here, winds its way around, travels down in here, and eventually goes into the River Yare, which goes all the way out to Yarmouth, or Yaremouth, which is how Great Yarmouth gets its name. And rivers were really good places for early settlers to move close to because they're very defensive, but mainly good for transport of goods. You've also got these areas of woodland up here. This is Mousehold Heath up in the north of the city, which it potentially could be planted. I mean, it's largely not planted. I think most of it is natural. But however, there are areas of planted forest, for example, Thetford, southwest of Norwich in Norfolk, which is one of the largest plantations in Europe, and it's mainly conifer trees. So that really is all the content that's required for section A. Remember, it's only 6 marks worth. Section A, question 2, is about coastal landscapes, and it's worth twice as many. It's worth 12 marks. 8 of those 12 marks are going to come from one question, the 8-mark examine question. I do have a separate tutorial for 8 markers made easy with lots of advice and how to structure it and practice questions to look at as well, so please feel free to look at that when you've got time. But when it comes to the content of coasts, there's also another 4 marks that could well be asked about from the content, so we'll go through that now. So the first thing you may be asked about is geology type. And when we talk about type of geology, for coasts, we're not so much interested in igneous and metamorphic and sedimentary. We mainly put it into 2 categories of hard and soft. So hard rocks, generally igneous metamorphic rocks, or soft rocks are the sedimentary sort of sands and clays. And the difference between the two, obviously, hard rocks are far more resistant to erosion. So coasts don't erode in those areas as much, and you get steep, high, rocky cliffs, features like wave-cut notches and wave-cut platforms, cave, arches, stacks, all of those bits and bobs form in hard rock areas, nothing like Norfolk, which is much more soft sedimentary rock. So they're much more easily eroded by the sea. So Holderness and Haysborough, 2 places very well known for eroding quite considerably. The cliffs are less steep, smaller, they tend to have more slumping material, and features like bays can form where there are different rock types, but largely we get quite nice wide beaches. So that's about geology type, hard or soft. Geological structure is the next thing. So when we talk about structure, it's not just about the type of rock, it's about how that rock is laid down. So where you've got different types of rock, you can either have a concordant or a discordant coastline. So concordant coasts are where the different geologies line up running parallel to the sea, and that can form things like coves or offshore bars. Discordant coasts we're much more interested in, because that's where the geology lines up running right angles to the sea, and it makes things like bays and headlands. They can later become cave arch stack stump. And just to show you the difference between the two in an image, here is the Dorset coastline. So this is Studland Bay, Swanage Bay, with your 2 harder resistant sort of limestone and chalk rocks there, which stick out as headlands, and the bays in between. So that's a discordant coastline. A concordant coast is where you've got the line that runs parallel to the sea as well. Okay, so this area is less likely to do as much erosion, unless it does have the next feature, which is things like joints and faults. So joints are small cracks and faults are bigger cracks in the rock. And when we talk about a faulty good or a faulty product, it's a weakness in that product. So faults are essentially weaknesses in even hard rock, which allow the sea to exploit it by things like hydraulic action, abrasion, that sort of stuff. So that's geology structure, and this shows you this is a very hard chalk rock. This is Flamborough Head, and this is chalk, but the chalk is sedimentary rock, so it's got bedding planes where the layers are built up, and it's got lots of joints. It's well jointed, which means it can easily be eroded by hydraulic action, abrasion, and by freeze-thaw weathering above the waves. So now moving on, these are the next things to do with coast you need to be aware of, the physical processes that act at the coast, and we're going to go through each of them separately. You've got erosion, transportation, deposition, mass movement, and weathering. So beginning with erosion, and I've lumped in destructive waves here as well. Erosion, you may have heard me or another teacher saying hydrographs. What we mean is, it's just a short way of remembering the 4 main types of erosion at the coast. Hydraulic action, which is the force of waves crashing into the cliff, compressing air, breaking up the rock. Abrasion, where waves carry beach material and sand and rocks and throw them against the cliff, wearing them away like the sandpaper effect. Attrition, which is where pebbles and rocks collide with each other and break into smaller pieces and become more rounded. And corrosion or solution, which is the one we use, which is when cliffs sort of dissolve by slightly acidic water, because most water is slightly acidic because it has carbon in it, which makes it carbonic acid. But only certain types of rock really will erode by solution. We're not so interested in this other than just to know it's one of the 4. So destructive waves, they occur when you've got generally higher winds and stormy conditions, and they have more ability to do these things, to erode more. So a destructive wave is something which breaks more frequently. There's normally 10 to 15 every minute. They're plunging, so they tend to create a more steeply sloping beach as they plunge, and they've got a very strong backwash to carry material away. So in winter, and the other element you need to be aware of is how does seasonality affect the ability of a coast to erode. So during winter, and most of these things are worse in winter, because winter is where there's more storms, there's more high winds, so there's more destructive waves, so there's more erosion potentially. So parts of the east coast, for example, Holderness, will erode up to 10 metres per year if we get a particularly stormy winter. So transportation next, including longshore drift. Now longshore drift, critical when it comes to coasts. Not at all important in rivers because it's not relevant, but in coasts very important. So your basic methods of transportation are trasal, sasol, traction, saltation, suspension, solution. Traction, big material rolled along. Saltation, smaller pebbles being bounced along. Suspension, small enough bits to be carried in the river and in the waves, and solution, dissolved material. But longshore drift is much more important to get your head around. So all of this stuff happens when longshore drift's happening, but longshore drift is this overall movement of sediment along a beach. Now it starts with the prevailing wind, the way the wind normally blows, and the swash follows that exact same movement. So the waves crash onto the beach with a swash, and then gravity pulls them straight back. So on at the beach at an angle, straight back under gravity, and that carries on. And this zigzagging shows an overall movement, of longshore drift down the coast. And if you get a change in direction of the coast, that's when you get certain features such as spits and bars forming. More on that soon. So deposition is the next thing, and again I'll include constructive waves into this as well. So deposition occurs in coast and rivers by the same process. Essentially, it's when energy goes. So when the waves or the river have less energy, you're more likely to have deposition. So we're interested in the reasons why waves get less energy. So as waves get their energy from the wind, if there is less wind, there will be less energy, so there's more likely to be deposition. So if the waves enter a sheltered bay where the headland stops the wind, then they're weaker and they'll drop their sediment. If the water becomes shallower, so if they get slowed down from the bottom of the wave, there's more friction and therefore weaker, so they drop. If there's lots of sediment in the waves, if it's carrying lots of material, say a big slump goes into the sea, it cannot carry all that sediment at once, so it's too heavy and therefore it ends up dropping some of it. And then if the river meets the sea, both of the flows are going the opposite direction, so the waves are weakened and they'll deposit, as will the river when it does the same. Now constructive waves often deposit material, and that's largely because they're not very powerful waves. They tend to sort of dribble up in the swash. They've got generally a more powerful swash, so more ability to put sediment on the beach than the backwash, so they don't take much away. Also, they're very infrequent, less than 10 a minute normally, and they don't plunge at all either. So these are gentle, nice gentle beaches, the sort of waves that create a very peaceful atmosphere at the coast. So mass movement next. Mass movement, and a definition of mass movement, is the movement of large amounts of material, hence the mass, at once under the force of gravity. So the movement is always downhill, and gravity is the only thing moving it. So mass movement tends to move weathered material, the loose material, as a result of rainwater and gravity. So rockfalls are one example where you find hard geologies where freeze thaw is happening up here. Eventually, or maybe even root penetration at the top, eventually the weathered material will just succumb to the force of gravity and fall. And if you get big piles of it clustering at the bottom, that's called a scree slope. Landslides are similar to rockfall. It's just where the bedding planes of sedimentary rocks like limestone or chalk run because of tectonic processes at an angle, which means that big chunks of land can slide under the force of gravity again down the slope onto the beach. Very dangerous if you want to be on a beach with this happens. Wear a hard hat. And this stuff, now this is slumping. Slumping is just the same as you slumping in your chair. It's where you've got sort of weaker geology, soft sands and clays. They get wet, very wet and saturated from rain above, and then they get undermined by waves below, and they slip along a slip plane, something like clay, and they just kind of slump down. And they characteristically see these sort of stepped grassy profile because the stuff still grows in the cliff material. That happens lots at Haysborough and at Holderness as well. Now again, how weather ties into this, mass movement events are worse in winter. The reason being there's much more rain, and all of these rely on rain to lubricate or to create freeze-thaw weathering. It's also much colder, so again freeze-thaw too, and there are more waves attacking the base, so again slumping is more likely in those cases. And now finally, weathering. Now weathering, just as important because it's involved in mass movement, but weathering can be physical or mechanical, chemical and biological. Now, physical just means any process that doesn't involve living things or chemical reactions. So water can lead to physical weathering, freeze thaw. This bit of gravity I'm going to take out. Okay, gravity, no, because gravity is involved in mass movement events. So when you've got this plus gravity, it's a mass movement event. Chemical weathering can involve things like rust. Rocks contain iron ore. That can rust if it gets wet, is exposed to oxygen, iron oxide. Acid rain, and even just acidic seawater, so carbonic acid in seawater, can cause chemical weathering. And then anything living that can weaken the rock in situ, so roots of plants and animals burrowing, that sort of stuff, is biological weathering. So the other thing about physical weathering, obviously known as mechanical sometimes, do just be mindful of that. If they say mechanical, they mean physical, they're the same thing. And again, that's worse in winter because there's more cold weather, so more potential freeze thaw can happen, and also there's more water too. Now, all the ingredients you've just been given with regards to geology and physical processes are really, really useful. And when you have got those in your brain fixed, you can now describe any coastal landform. So a coastal landform is any feature of a coast that's been created through geology, whether it's hard or soft, the structure of that geology, and those physical processes working together. Now, if there's largely erosion, you can get cliff and wave cut platforms, bays and headlands, or cave arch stack stump. And if it's mainly an area of deposition and transportation, so not so much erosion going on, you'll get features such as spits, bars, and beaches. So there is a strategy to answer these sorts of questions, which will help you just make sure you get all the processes involved. If you start with the geology, if you talk about your first sentence is it hard or soft geology? Is it concordant or discordant coast? Are there joints? Are there faults? You can then look at the physical processes, so what the pick a mix, so the weathering, erosion, mass movement, and pick which ones are relevant to help you explain how that thing was formed. So try and get at least 3 or 4 different factors for any landform. But also look out for examine questions. The 8-mark examine question has in the past used landforms, and again there is practice for that in a separate PowerPoint. So the same process can be used roughly for rivers, not quite the same, but close enough, and I'll show you all of these in the next few slides. So for any one of these landforms, and the first one is cliffs and wave cut platforms, what I've got is a starter slide which gives you the strategy, so talk about the geology, talk about the physical processes, put it all together. I've included a little summary of the physical processes here, and then a diagram to help you maybe describe it. Well, what you may want to do is have a go at explaining the formation of the features that you see. So I've done it for all of them, so at any point if you want to have a go yourself and then see if you are right, you can pause the screen now. For those of you wanting to see how it works then, or getting the answers, then I will carry on with that, and I'll do that for all of the landforms for coast and rivers. So for coasts, for cliffs and wave cut platforms firstly, the geology is hard. You can see that this is a steep cliff, it's rocky, it creates a steep profile. So cliffs and wave cut platforms are formed in hard geology, e.g. chalk. So in yellow I've highlighted where I've mentioned geology. Hydraulic action, the force of water compressing air in cracks, from destructive waves between high and low water tide makes a wave cut notch. So that's one physical or 2 physical processes. I've mentioned hydraulic action and destructive waves. An overhang is formed, you can see that here, which is weakened by biological weathering from above. So again, you can see plants growing there, root action, biological weathering. Now I've mentioned geology, erosion, and weathering processes. Eventually, rockfall mass movement can occur under the force of gravity, causing cliff retreat. So what I've now identified is that you've got this notch, you've got an overhang created and weakened by weathering, and this is collapsed mass movement event, and that's led to the cliff retreating. After repeated cliff collapse and a wave cut platform is left gently sloping out to sea. So this little feature here is just that final sentence. This is what's left over once this has happened a few times. Okay, so that's how it works, and you can see all the yellow shows you all the different physical processes I've got: mass movement, weathering, and erosion, as well as geology. So I've got 3 different processes plus geology in there. So if you want to have another go or attempt this one yourself, now you've practiced, this is for bay and headland. Again, you've got your menu you can use here. Aim for 2 or 3 from the menu physical processes, plus mention geology to start with. Okay, so if you want to have a go, do that now. If you want to just pause it, and for everybody else, I'll go through the answers. So starting with geology, bay and headlands occur in areas of discordant geology, so hard and soft rock alternating, you can see here. Destructive waves, erosion, can erode the coast through hydraulic action, compressed air in cracks, and abrasion, sediment thrown at cliffs in waves. Remember, I haven't just mentioned the process, I've just very briefly described what that process is, so I can show the examiner my knowledge. This erodes the soft rock faster, creating bays, and the harder rock leave headlands sticking out to sea, which is what we can see here, headland, bay, headland, bay. Now, I'm a bit limited for my different types of processes here. I've only really mentioned erosion, so just destructive waves, hydraulic action, abrasion. So I'm going to add another one because I can. In bays, the wind is blocked by the headlands. Okay, so these headlands will block the wind, so deposition can occur to form beaches. Okay, and that's where I can get an extra process in there. Now again, if you want to have your own go, by now you should know the way it works. I will let you pause it, and then I will give you the process for those of you who want the cheat. So, in areas of hard geology, e.g. chalk, where the headlands have been created due to a discordant coast, I've mentioned geology and geological structure there. Faults in the headland, third one, can be eroded as air is compressed in them by hydraulic action. So again, I've named it and described it, creating caves. Further erosion from sediment in waves, or abrasion, can erode them through the headland to make an arch. The top of the arch can be weathered by biological weathering or root action. Eventually, massive movement event like rockfall can occur under the force of gravity, leaving a stack, which is further eroded at the base by destructive waves, leaving a stump. So again, there's loads in this one because there's loads going on from this all the way to the stump there. Now, these are particularly difficult when it comes to looking at geology. These are the landforms of deposition and transportation. So spits and bars I've put in the same description because exactly the same thing happens, just becomes a bar maybe right at the end. Okay, so again, if you want to have a go at this one, same process, then please feel free to pause it now. So spits form firstly when there is a bay, usually from discordant coasts. That's how I've got around the geology section. So a discordant coast has created this change in direction, which means that we've got the conditions ready for a spit to form. Sediment is pushed onto the beach in the swash, which can hit the beach at an angle from the prevailing wind. This returns under gravity in the swash and zigzags along the coast via longshore drift. Now, I've only mentioned longshore drift there, but really I've mentioned it and described it in decent detail so the examiner knows that I know what longshore drift is. If the coast changes direction, as it has here, longshore drift continues across the bay in shelter or due to a river entering the bay from the land. The wave energy is reduced, causing deposition. So that's important. To get this spit to form, you need the sediment to be deposited, and that could be because of shelter from the bay, less wind, or the river flowing, reducing the flow. This can build more as the sediment makes the bay shallower still, eventually making the spit. So as this sediment builds up to begin with, it makes it shallower, so that increases friction as well. Sediment from the river is trapped behind the spit, creating a salt marsh, here, where the little photo is. If a river is not strong enough or not there, sometimes the spit can travel across a bay and rejoin land, forming a bar. So that is literally the difference between a spit and a bar, that a bar goes all the way across and rejoins the land. Now this, I think, is probably the most challenging landform of coasts to describe, purely because there's not loads of clear features going on. You can see from this image there's quite a bit more than maybe you've been taught in lessons, but essentially you've got a few ridges towards the back of the beach, which we call a storm beach. Now they only really occur in the very highest waves, hence why they're at the back of the beach. Most of the time the water only ever gets to kind of here. So that's high tide mark here. The very highest of tides, this maximum spring tide, is here, and that's where you tend to get your biggest, more destructive waves, and that's why there's this ridge. It's scoured out. So getting the geology done is also a bit of a challenge with these. If you want to have a go and see if you're right, time to do it is now. And I'm just going to give you the answers from this point forward. So beaches form in areas of coast due to sediment build-up in waves as a result of weak geology cliffs. So to form a beach, you need sediment, and that sediment needs to be in the waves. That sediment has to come from somewhere. So I've mentioned weak geology cliffs like sandstone or clay, and those sandstone cliffs have been easily eroded by mass movement events like slumping, and it's chucked a lot of sediment into the beach or into the sea, which is now going to form the beach. So this can be due to being in a sheltered bay, meaning waves lose energy and deposit, or as a result of constructive waves with a stronger swash than backwash. As beaches build up, they can increase friction, so they add to deposition, the bottom. Beaches can also often contain features like ridges or storm beaches when high winds push destructive waves high up the beach. So I've mentioned erosion as well, even though it's a landform of deposition. The plunging action and strong backwash means steep ridges are formed and beaches are eroded. So there you go. I've mentioned a few things about beaches, but looking specifically at features. Like I said, this is the hardest one to have to do, so hopefully you won't get that in an exam. So now we've looked at the landform of coasts, we're just looking at the impacts of coastal recession and flooding. Now I've put those in bold because the question might ask you specifically about recession, which is the retreat of the coast and erosion, or it might ask you about flooding. So that's mainly to do with coastal flooding due to sea level rise or from storm surges, like big storms like happened in Cromer in 2013, I believe, and damaged the pier and everything there. So most of the impacts you get of effects of coastal flooding and recession, we are mainly bothered about the ones that affect us as humans. Okay, so remember, flooding and recession, they are different, don't confuse them. Impacts are either classified as socio-economic impacts, i.e. they affect people and jobs and money, and they're the ones we're mostly worried about, or environmental impacts, so can affect habitats and species. Now of these, there's only one habitats and species one, which is this one, so I'm just going to highlight that and raise them up a little bit. The others are, generally speaking, to do with socioeconomic problems, and that's the reason that we mention those and highlight this, is because at the coast, erosion and flooding, generally speaking, we're worried about how it affects us. So what do we do about it? That's the thing. So you need to be aware, by the way, of a variety of things. That's why I've given you a variety. So loss of homes, disruptions of roads and railways or infrastructure, decrease in property value, loss of businesses, cliffs can be dangerous for people like walkers, increased deposition, downdrift. So again, that can be a consequence of coastal erosion. It can mean that there's more sand deposited. That can actually be a good thing. And then habitats are destroyed as the cliffs retreat. What do we do about it if this is happening? Because obviously most of these things are very negative. Well, we've got a choice. We manage the coast 4 ways, and it's mainly the decision made by local governments. So if you've got a coast as part of your local government, so North Norfolk, for example, they'll get a chunk of money from the Department for Environment, Food and Rural Affairs, or DEFRA. Now, they're a government department, and they, alongside the Environment Agency and local governments, decide what we do along any stretch of coast. So if we take North Norfolk, which would include Cromer, and include other areas like Overstrand, we either decide to do nothing. So no active intervention is the posh way of saying do nothing. That means we just let nature take its course, really. If you live in a no active intervention zone, then it means that your house won't be protected and you'll get no compensation. We can do managed retreat, which is slightly better than doing nothing. That's where you let the current defences fail, and slowly, but you don't replace them, and maybe you allow people to maybe have a bit of compensation. The value of their homes, maybe part of it will be given to them or help them relocate. Neither of these is particularly popular, but essential. When you've only got a small amount of money to cover, you don't want to protect the places that are less valuable. For places like Cromer, which are more valuable, have a lot more people, a lot more industry, we have the process called hold the line going on. That's where you hold the existing current defences as they are. If they get damaged, you replace them or you repair them, as happened in the 2013 storm surge. And rarer still is if you want to protect a place long term and it's not currently got sea defences, is you build brand new ones there. So that's called advance the line, and you try and help build up the coast. That happened actually in Sea Palling when they built offshore reefs, and it increased the size of the beach, but this is very rare because it's often quite expensive. So for these last two, you've got a few choices. If you've chosen to hold the line or advance the line, you can use these types of management. Now, soft engineering or hard engineering. You need to know a definition of each. So works with the natural processes, and that's soft engineering. Hard engineering requires unnatural construction or disrupts natural processes. It doesn't really work with them. So anything artificial looking is hard engineering. So for each, you need to be aware of 1 or 2 strategies. So I've given you those on here. You don't need to be able to draw a diagram just to show you what they look like, but you need to know what they are and how they work. So beach nourishment, lorries or boats dump new sand onto the beach to replace the old sand lost via longshore drift. Offshore reefs, which actually don't look very natural, but the beach they create is a natural thing. So that's where you put big rocks out to sea, and that reduces the wave energy before it reaches the coast and creates deposition. Sea walls, concrete walls placed in front of a cliff to absorb the wave energy or reflect it back. Excuse me. Often you won't notice these because you'll think they're just a promenade, and they're used as a way for pedestrians to walk. Groins, they can be wooden or rock groins, and again they try and stop longshore drift from occurring, just a bit like this really, except this is building up a beach. They build up a beach by stopping the beach getting carried away. And lastly, riprap, which is where you put big boulders again in front of the cliffs or in front of a seawall to protect that from the wave energy. So for each of these you need to know specific advantages and as specific as possible. So if you know how much it costs, or you know how long it lasts or anything like that, or a place that has it, it's always worth knowing and using. Be prepared that a question might ask you to extend these advantages, or it might say explain the advantages of soft engineering. You should mention one. Say what one of the advantages is, or say what it is, what an advantage is, and then say this is good because. So try and extend these answers, any advantage, disadvantage. One thing I would do with this slide, if you want to extend your learning a little bit, is take that and see if you can say this means that and add a bit more onto it. Apologies if you can hear a hoover, there is a cleaner now in the classroom. So the case study we use for the coast is Holderness in East Yorkshire. This is a good case study because it's got a lot of physical and human processes going on, and there's a big amount of change going on. So the location of Holderness is mostly soft boulder clay. So the geology is mostly soft boulder clay, easily eroded, prone to slumping after lots of rainfall particularly, and in winter time. But not all of it. Some of it is actually harder chalk. So up here you can see a headland, very clear Flamborough head sticking out. That is very resistant chalk, and you can see that it's much more resistant because it's created that headland. So that's up there. Now, physical processes that act along this coast are coastal erosion, all the types of erosion: hydraulic action, abrasion, attrition, solution, from strong waves in the North Sea, which is here, and large fetch. I say large fetch, fairly large fetch, not as big as other fetches, but still big enough. The weak geology also means the erosion is fairly rapid, in some places up to 10 metres a year. Not everywhere, but some places. The boulder clay and also the rainfall mean that slumping is very frequent, so the waves attack the base and the top gets very wet and slumps into the sea. And longshore drift is happening a lot. So you can see, as you follow it down to the south area with this zigzagging going on, you can see this would be the prevailing wind direction. That zigzag movement, which is very poorly drawn by me, has led to the formation of Spurn Head Spit, which is a very nice natural feature. There's a road and a lighthouse station, a lifeboat station, sorry, over on Spurn Head. Now, human processes acting here, there are lots. I mean, all of these towns, for example, are managed to some degree or not, so they will use one of the 4 management processes. At Mappleton, they've actually got hold the line. So what they've done is they've built a rock groin out to sea to prevent longshore drift as the sediment travels this way, and that has built up the beach at Mappleton to protect Mappleton town. South of Mappleton, that's actually starved the area, and the erosion rates have increased here by up to about 10 metres per year, which is not great. Agriculture as well is occurring on much of the land, so as well as management of the area, we do compact the land, tractors driving on it all the time, so that has an impact on the economy, but also it means that we're putting extra pressure on it. And the other thing that's putting a lot of pressure on is all those squares there are urban settlements. So alongside your urban settlements, you've also got industry, tourism, like caravan parks, all placed with a nice sea view next to the cliff, all putting lots of pressure on the land here. These dots, by the way, they're all towns that were once on the land but have now been lost to the sea. So you've got Great Colden and Monkwell that have all been gone now, unfortunately, because of the erosion. So this was where the coastline used to be in Roman times. Okay, so that summarises coasts, and now looking at the final part of section A, which is rivers. Thank you for bearing with us this far. So the benefit of rivers is that it's structured exactly the same way as coasts. There's 12 marks, there's an 8-mark exam and question at the end, and again there's a tutorial to help you with those, with examples, and there are 4 other smaller based marks for the rest of the content, which again is fairly extensive relative to the amount of marks it's available. So the first thing you need to be aware of coasts is that the river, from start to finish, from source to mouth as we'd say, you need to be aware of how the river changes. So this shows you the overall river profile on side view, and you can see the upper course, which is the first sort of third of the river, is the steepest section. It's where you get your waterfalls and V-shaped valleys and interlocking spurs, and it's where you've got a V-shaped kind of quite narrow valley. Into the middle course, it gets less steep in terms of gradient, mainly sort of transportation happening. You get meanders that occur, and oxbow lakes can occur here too, and the valley starts to get a bit less V-shaped and a bit wider. And then finally, as you get nearest the sea, you've got almost mainly deposition going on, so very little erosion. Now, the erosion that happens is going left to right, so around that way, rather than going down, and you can get things like floodplains and levees occurring here. So the changes are really summarised nicely by this. This is the Bradshaw model. Now, Bradshaw model just shows you, this would be upstream means the source and this means the mouth, and it shows you by the shape of the triangle whether the thing is increasing or decreasing. So discharge, the amount of water in the river, is increasing quite a lot as the river goes downstream. All the little extra tributaries add to it. The width of the river, the occupied channel width, that's just the width of the river, it gets wider. The depth of the channel gets deeper. Again, more water has got to be fitted into a bigger space, so it's going to have to get wider and deeper to accommodate it. The speed of the river gets faster. Now that looks a bit weird because it gets less steep, but I'll talk about that in a second. The amount of sediment, the load quantity, gets much more. As it gets past more, it picks up more stuff. The size of that sediment gets smaller. And again, that's because of things like attrition, everything knocking into itself, making it smaller. So by the time it gets to the sea, it's almost just silty sludge. The roughness of the channel bed, i.e. how bumpy lumpy it is, gets much smoother as you go down, again because of more erosion. And the angle, the gradient, goes down like we've mentioned before. Now, it's because of the size of the particles, the channel bed roughness, and the slope angle that the velocity actually increases. So if you were just on a bike and this was a smooth track, you'd go fastest here because it's steepest. But this isn't a smooth track. This is a very lumpy, bumpy, off cross-country, off-piste sort of track. So if you were to cycle down that, you'd be slowed down all the while by going up and around the bumps. The river does the same thing. It slows right down because there's not much of it and it's hitting big sediment. As you get towards the lower end, this is now really smooth and straight and flat, and so actually if you're on a bike here, there's very few obstacles, and you've got a lot of space and a lot of smooth area to kind of cycle over, so that makes you go quicker. The same happens in a river, and not only that, you've got lots more water helping you force your way through, so the speed increases massively. I say massively, slightly, as you get downstream, even though it might get a little bit less steep. So with all this in mind, then you may well get quite a big question on this particular thing because there's so many things shown in the Bradshaw model, and you just need to be aware of how it changes from one to the end, okay, from source to mouth. The other thing I'll mention, and this comes into the landform section, is gravitational potential energy. Gravitational potential energy is the furthest away from the sea level you are. So the higher you are, the more gravitational potential energy you have, and therefore there's more pull. So up here, the river is trying to be pulled downwards, and you get what's called vertical erosion, and that's why you get steep features like V-shaped valleys and waterfalls. As you get closer to sea level, there is less pull because you're closer to it, so more of the erosion is focused on going left and right, so it's called lateral erosion. More on that when we look at landforms in a second. So this looks fairly familiar. This looks a lot like the coast section, and deliberately we've chosen rivers to do rather than glaciation because rivers share a lot of the similar processes. So for erosion, rather than looking at destructive waves, because there's no waves, it's a river, we look at vertical or lateral erosion due to gravitational potential energy, and also the same erosion processes, hydraulic action, abrasion, attrition and solution. So all the same as coasts, so I don't need to go over all that again. the vertical or lateral erosion just illustrates. Vertical means downwards, lateral means side to side. Okay, sometimes called horizontal erosion. Transportation, again, I don't need to dwell on this. Exactly the same. You've got traction, rolling the boulders along the bottom, saltation, bouncing them, suspension, suspending them, and you've got solution, which is minerals dissolved in the water. What you don't have, because it's not, again, at the coast, is longshore drift. There's no wind interaction whatsoever. It's just gravity. Now, deposition is the third section. Now, that happens in rivers because of loss of energy, just like at coasts. It's just that the way that loss of energy occurs varies. So, rivers can burst their banks. That makes them effectively a very wide, shallow river. And because they're more shallow, there's more friction, and they'll deposit their material. Rivers get shallower because maybe there's less rainfall and there's more evaporation. So because, again, they get shallower, there's more deposition and more friction with the riverbed, sorry, and banks. When the rivers go round the slower inside bend of a meander, okay, going slower means less energy, means more deposition. And if the rivers meet the sea, or when they meet the sea, the waves, again, counteract their energy. So again, they deposit lots of stuff, often as an estuary or behind a spit as a salt marsh. There you go, you can see the inside bend of meander there building up over time, whereas the outside bend is eroding. And this is a river in flood, this is the main channel, and as it spreads out over here, this is very, very, as I say, very shallow. It's much shallower than the actual river channel itself, and so there's lots of sediment going to be deposited on this flat area here. So mass movement, again, don't need to dwell on this too much. Exactly the same mass movement processes you need to know as in coasts. It's just that they're happening on the banks of the river rather than at a cliff face. Okay, so rock falls with harder river geologies, mainly going to be found in things like V-shaped valleys in upland areas where it's colder. Landslides along a bedding plane, again, if it's orientated that way, less likely, but also rotational slumps. So sand and clay, the banks can go in. You can see that on this diagram here. This is a river, and the banks itself, you can see, are composed of soft geology, and it's slumping in several places. This is harder geology. This is the river Dove, and this is Thorpe Cloud in Derbyshire. And what you've got here, that looks like a pathway, but it's not. This is a naturally eroding kind of slope where you've got a scree slope piling down here, and then actually falling into the river itself and getting carried away by the river's flow. So that is through things like root penetration, weakening it, or maybe freeze-thaw weathering on cold areas because it's a mountain. Weathering, again, exactly the same. Physical, chemical, biological. Ignore the gravity. That's what mass movement's for. So, river landforms. So any feature of a river that's been created through the combination of whereabouts along the river profile it is. So is it upper, middle or lower course? So this is a bit different to the geology thing. This is more about how far away from the sea it is. So therefore more gravitational potential energy. Alongside that, you've then got your physical processes menu working together. So our upper course landforms, the steep ones because of more vertical erosion, are waterfalls and gorges and V-shaped valleys. Whereas the middle and lower course landforms, with flatter, wider, a little bit less dramatic, they are meanders and oxbow lakes, and floodplains and levees. So we're going to get onto these. The strategy you want to use here then to answer this and smash these questions is start with where it's found along the profile, upper, middle, lower, and comment on the gravitational potential energy, vertical or lateral erosion. Look at the physical processes, pick a mix, and pick as many of those as you think are applicable. So 3 or 4 different factors is fine. And again, they have asked 8-mark examine questions about this, but you'll find those in that 8 markers made easy tutorial to practice on if you wish. So at this stage, now you've practiced it for coasts, if you want to do it for rivers yourself, please feel free to pause now and have a go. The menu's here, the processes is there, the way to do it is there, and I will talk anyone else through it and give you the answers if you've attempted it now. So, waterfalls and gorges. Waterfalls form in the upper course of a river, so upper, where high gravitational potential energy means vertical erosion is dominant. Okay, so I've mentioned it's in the upper course, high GPE and lots of vertical erosion, which hence why it's going to be eroding downwards. As the river reaches a weaker rock, so geology is important here, it erodes vertically faster, creating a drop or a step, which increases the power of the river to erode by hydraulic action, the force of the water, and abrasion, rocks and pebbles rubbing against it, wearing it down. So I haven't described those there. I should have done that really. Abrasion continues to form a plunge pool, which would happen here, and the soft rock undercuts a layer of harder rock to create an overhang. So this hard rock is going to get undercut. You can't see the picture here, but hopefully you can click back and see. Physical weathering from freeze-thaw in the colder upland areas mean the overhang is weakened and mass movement by rockfall can occur, further increasing abrasion and causing the waterfall to retreat. After repeated collapses and a steep-sided gorge can be created, which looks a little bit like this. Okay, so as the waterfall moves and the top part, the cap rock, the harder bit collapses, it'll just move back and move back and move back and move back, eventually creating this steep-sided gorge either way. So again, if you want to have a go doing this for V-shaped valleys and interlocking spurs, you can. I'm just going to let you pause it now. Okay, so V-shaped valleys form in the upper course where high gravitational potential energy means vertical erosion is dominant. This is the same, except I've just changed V-shaped valleys from waterfalls. Rivers will erode downwards by mainly hydraulic action and abrasion, and again, describe those. What are they very briefly? As the river banks are exposed, these bits, they can be weathered by biological weathering, root action, and freeze-thaw weathering. The weakened banks can then move under gravity through mass movement events such as slumps or rockfall, especially when rainfall is high. This material then increases abrasion in the riverbed and deepens the valley. As rivers have less power to erode laterally, they wind around more resistant rock to form interlocking spurs. Because we're in the upper course, the power of erosion is vertical. So any harder rock that they can't go they can't go through, they will wind around, and that forms these things called interlocking spurs, which look a bit like this, or they look exactly like this. Okay, so the river, where these people are standing, there's a little piddle of a river going through here, and it winds around this side, and it goes back around this side, and it'll wind around these obstacles, creating these kind of zip-like interlocking V-shaped valley spurs. Okay, so now into the middle and lower course, so meanders and oxbow lakes. This is a cross-section of a meander, and you can see it's very much an asymmetrical profile. So it's got a deep section here on the outside bend, and on the inside bend it's very shallow. It's got lots of build-up of sediment. So it tells you straight away that erosion's happening here and transport's occurring here, whereas deposition is happening here because it's going a bit slower. So again, have a go, pause it, and I'll help you out. Okay, so meanders form in the middle and lower course of a river, middle-lower, where there is less gravitational potential energy and erosion becomes more lateral, so side to side. Any small bend in a river forces the water to move quickly around the outside bend, here, meaning there's more energy to erode by hydraulic action and abrasion, which I should describe, from suspended sediment and large pebbles through traction. So again, I've mentioned erosion and transportation methods there. The outer bend, therefore, is deeper and steeper, creating an overhang. There you go, and you can see the cracks are starting to form because of biological weathering. On the slower moving inside bend, the river has less energy and sediment is deposited, forming a slip-off slope, making the river shallower and increasing deposition. So as this area gets slower, it drops off the sediment. That makes it shallower, and that increases friction, which drops off even more sediment, and that builds up. Now that happens again and again and again in a meander if you don't manage it. So with continued erosion outside and deposition inside, meanders become more sinuous, that means more wavy, and their neck can break in a flood event, forming a straight channel, leaving an oxbow lake. So this picture is just going to show you what that looks like. Okay, so here you've got your eroded section on the outside bend, and then your deposition on the inside bend, and then it curves around. So this outside bend is eroding and the inside bend's depositing, and again it's whipping round here, and these areas here, because they're eroding, they're both going to meet eventually in the middle, and you can see that happening here. So as they've continued to erode and deposit, the meander has shifted, it's become more sinuous, it's more wavy, and eventually one flood event will break through this little narrow neck and it'll straighten the river by itself. Then you'll get deposition here because the flow stops, and because the flow stops, it deposits, and eventually this oxbow lake, which is what this bit is, will actually fill up and just become like a bit of woodland or a bit of grass or something. So you'll tend to see that as a meander scar, but that's an oxbow lake currently. Okay, floodplains and levees, often the more difficult, the most least memorable of all the different river landforms. Again, same process, have a go. Alright, so floodplains and levees form in the lower course, where there is less gravitational potential energy and erosion becomes more lateral, and also there's mainly deposition. After several years of meanders eroding laterally, so we've talked about meanders first, through hydraulic action and abrasion, describe those, they carve out a wide flat area. So if you imagine this river just goes left and right over thousands or hundreds of thousands of years, and it creates this flat area. You can see where the river hasn't migrated, there's a little area called a bluff line. That's a higher area around it. So this area is the sort of flat floodplain area. So any flood that happens, this river is going to spill out onto it. So when rivers burst their banks, it increases friction, so sediment transported by suspension is deposited in the flat area and builds up. The larger and heavier sediment is deposited first because it's the largest and heaviest. So that goes next to the river, and after many flood events, so repeated flood events, that's really critical when you're talking about floodplains and levees, they'll pile up to form a raised bank beside the river called a levee. And I'll just go back to show you that in the diagrams again. So what you've got here, you've got your meander that's carved out this area. The flood occurs, the smaller stuff gets carried further, the bigger stuff closer, and then after several years, thousands of years, that will create this steep raised area called a levee, and this area here is a floodplain. It's very flat, it's very fertile, great for farming, not great for building houses. Okay, so how weather and climate affects rivers. This really is generally, is it hot, cold, is it wet, dry? That's what we mean by climate, the temperature and the amount of rainfall. So when it comes to hotter climates, because there's more evaporation when it's hot, it means the amount of water in a river gets lower. And because it's lower, there's less velocity, less speed, and less energy, so you get more deposition. So that increases deposition in the river. Colder climates can actually have the same effect if it's frozen, but generally speaking you're more likely to get more freeze thaw. So because it's colder, there's more sediment going into the rivers, and again, more sediment means it can deposit more as well, so you might get extra deposition here. When it's drier, exactly the same, less water in a river to erode. So if it has a particular period of less rain, even if it's not hot, if there's less water going into the river, it reduces the ability of the river to carry stuff, so slower velocity and more deposition occurs. And in wetter climates you get the opposite to all these things. So because it's wetter, the rivers are full, they've got loads of energy, they can carry more sediment, they can erode more, and they tend to increase erosion, but also they can transport more sediment and widen and deepen the rivers at the time. So if you look at very hot, very cold, very dry, very wet climates, it can affect a river in different ways. Rivers are very, very prone to change in different weather conditions. Okay, and the other thing about weather, because of climate change, it is changing in the UK, and river flooding risks are increasing. So we're having more storms, which means we're getting more water, making it more likely to erode areas. Also, we're getting increased long periods of hot and dry weather, so we get deposition. And when you get deposition in rivers, followed by a big storm, that river, which has now got loads of deposited material, is less able to hold the more water that's coming. So it's going to increase flooding, and that's a real problem for us. So colder periods also mean soil becomes impermeable because it's frozen, and snowmelt just goes straight into the river when it thaws. So we've got these extremes are not good for rivers or for us, because it's more likely, all of them are more likely to lead to flooding along the way. Even the dry, hot weather, because of more deposition, meaning the river can hold less material. So human activity, and where human activity can affect rivers, the options here. Okay, the answer can only be, and it's about, remember, we focus our human activity in rivers on agriculture, industry or urbanisation. So farming, making of products and factories and things like that, and maybe tourism industry, and urbanisation, building houses and settlements. So the answer for any of these things is agriculture, industry or urbanisation. So if you want to have a go, read through the change that's going to occur and tell me whether you think that's mainly the fault of agriculture, industry or urbanisation. If you want to pause it now, I'm going to reveal it in 3 seconds. Okay, so Agriculture, when you've got drainage ditches, it can move water very quickly into streams. The idea is you drain the land to make it better for growing crops, but it overwhelms the river. So it can destroy the natural wetland landscape, but it can also mean the river is more overwhelmed and more likely to flood. Other agricultural things are where you deforest areas. You chop down trees to make farmland space. That reduces interception and you get more runoff and increased river discharge. Abstracting water for irrigation, so for watering your crops, you can actually take water out of the river and affect it, so you get more deposition. And ploughing fields, if you plough the fields up and down the slope, you create these, it's almost like a slide for water to run through. So mostly when you manage fields near a river, you try and plough them across the slope rather than up and down it. So agriculture, you can see, affects rivers quite a number of ways. Urbanisation mainly affects it in a couple of ways. Firstly, we build impermeable surfaces like roads, concrete, all those sort of things, which reduce infiltration, so reduce the ability for the water to soak into the soil, and it increases runoff. So that can lead to river flooding, and more on that in a bit. And houses are built on floodplains, which is really stupid, but we still do it, which again reduces that infiltration and increases, it's a typo there, surface runoff. And lastly, industry. So industry this is now more about polluting the river and making the river poorer quality. Chemicals or waste products can be spilled or dumped into them. That also is true with agriculture because they use fertilizers. And also industry can use lots of river water. So if you want to create energy, for example, it's a massive amount of water used for creating energy. And again, that can reduce discharge, increase deposition, and again, generally lead to more flooding potential. But again, flooding is going to be a section very, very soon on this, as you can see. So flooding, the cause of flooding, I've colour coded them for you. There's natural and human based causes of flooding. Now you need to be aware of the cause of flooding specifically, because you may well get it could be an 8-mark question, you don't know, but it might show you a landscape where it asks you that might be labelled, and it might ask you to pick out some of the human and physical causes of flooding, or assess the human and physical causes of flooding, in which case you need to be aware of that landscape, what is the one that affects flooding the most. So Boscastle is a good example of a place that flooded because of several of these things. It was a very steep valley with impermeable rocks. They'd deforested areas upstream. They'd also built storm drains in a settlement near there, and it occurred after intense rainfall. So all of these factors added together to create a really, really big flood in Boscastle. Now I've just cheated by accidentally clicking the impermeable rocks to show you how they match up. So impermeable rocks, such as clay, do not allow water to pass through them, so it reduces infiltration and increases surface runoff. Now you can see all of these have been done for you and explained. You would need to do this explaining as part of your exam question. This is going to be an extended question. What I would also say is that this is something which would often be an outline question in a paper. Might be worth maybe 2 or 3 marks, where it says outline a cause of river flooding, or a human cause or a physical cause. Once you've named the physical cause or the human cause, these are human causes, the blue, and the yellow is physical, the orange is physical. Once you've named it, that's worth 1 mark of maybe 3 or 4. You've then got to be able to describe how it causes flooding to get the extra marks. So impermeable rocks, such as clay, do not allow water to pass through them, so you'd get the mark for impermeable rocks. Mentioning clay might get you a 2nd mark, but not sure. But by saying what impermeable rocks are, don't allow water to pass through them, that's 2 marks. Reducing infiltration and increasing surface runoff is either 3 or 4 marks. So you can see how you can explain these away to get to flooding by getting maybe good marks there. Okay, so I'm going to let you, I'll match those up for you, and if you want to try and see if you can match them up yourself, then do it now before I do it. Okay, so steep valley sides. Again, that's about how steep the slope is, more likely to get there faster, less infiltration, more surface runoff. Take the vegetation away or deforest the area, less interception, less infiltration, more surface runoff. Building on floodplains, again, no infiltration, impermeable surfaces, more surface runoff. Climate change, flood risk increases because of warmer climates and more storms and more extreme events. Intense rainfall, so long intense rainfall, again, too much water at once, less infiltration, more surface runoff. And snowmelt as well. Okay, so snowmelt, lots of water when it goes above freezing all at once, and the ground is still frozen, so it can't soak it all up. There you go. So have a little look at those and pay attention to those before we move on to the next section. Storm or flood hydrographs. Now, there was an 8-mark question which did use storm or flood hydrographs. Again, it's an example in the 8 markers made easy tutorial. This shows you a graph of a few things. Firstly, the bar chart bit. That's a rainfall event, or a storm, if you will. And what you've got is the peak of the storm, excuse me, in this hour, or this hour period, it got up to about 50 millimeters of rainfall in that period of time. So that's the peak. Now, what you see, excuse me, when you see this peak occurring in the river, that shows you how long it took for this amount of rainfall to reach the river, because it makes sense that where the river is at its highest is when the rain was at its highest, but just sort of how long it took. So the lag time is the period of time it took from the high amount of rainfall to get into the river. Now, you don't want your storm hydrograph to look like this, because this spells trouble. This looks like flooding to me, because if an area goes above this dotted line, and every river will be different, it might be down here for some, it might be up here for others, but if it gets beyond this section, it means that the river's burst its banks and it's in flood. So you want to try and keep this rising limb from going above this dotted line, and the way to do that is to manage your river, because if the rainfall event is the same, it's going to affect it the same way unless you change something. If this was a different area, if this was a forested area, you might find that there's more interception, and there's more water being absorbed by the roots of the trees. So what's going to happen is that actually the stuff that's falling out the sky is less likely to find its way into the river as quickly. It's going to take its time, because it's got to negotiate all the leaves and all the roots and all the things that are trying to use it. So that's going to slow down this water and spread it out over a longer area, and by the time it's got to here, it's dealt with it more easily, and therefore it's going to start to sink this way. So it's not going to reach bank full discharge. So flood hydrographs can vary. The shape can depend on what the drainage basin is like, and you've got different examples there. So in terms of the size of the drainage basin, if you've got a big one, more water in it, it's likely to take longer to get into the river, but when it does, there's going to be more water in it. If it's a small drainage basin, it'll get there quickly, but it won't be as high. Okay. If you've got a vegetated area, so if there's lots of forest, you can see, look at the effect that has on the discharge. It goes up slowly, it reaches a smaller peak, and it goes down. So if you've got a bare area, it goes up very quickly, incredibly steep rising limb, we call this, and that again is more likely to flood. If you've got a steep valley side, again, the steeper the valley, the quicker it'll flow, just like the last slide. So if you link this particular storm hydrograph to these things here, each one of those areas impermeable rocks. What do you think it would do? It's more likely to create a steep profile, because it can't soak in, so it runs straight off. Anything that increases runoff will increase the steepness of this rising limb. So that's the valley side steepness. Soil type, if the soil is impermeable or the rock is impermeable, then it will go up very steeply. If it's permeable, it will take its time soaking in. So all of these factors affect the shape of a storm hydrograph, and you really want it to be the green, generally speaking, rather than the orange. Even though this one is large, it's the lag time that we're after. It's taken a longer time to reach its peak discharge, and therefore it's more able to evacuate people, or the river is able to deal with the water more easily. Now, if you find yourself in a situation where your river is likely to flood, there are a few things you can do about it. Just like coasts, you can do soft engineering, working with natural processes, or hard engineering, so requiring unnatural construction, concrete, things like dams and embankments, that sort of stuff. So soft engineering, the criticisms of these are generally kind of more than the advantages, although it does look a lot nicer. So one of the things is floodplain zoning. That's where you literally don't stop the river flooding at all, you just put the stuff that's more valuable further away. So the housing and industry is higher up, further away from the river. Car parks, playing fields, pasture, and then the areas that you just want to avoid completely, just they're the ones next to the river. If the river floods a little bit and your sheep have to stay in the shed for a bit longer and you feed them some hay that you've got from your winter stocks, then fine, it's not the end of the world. By the time the flood's gone down, they can get back out there. Whereas if your house floods, then it's catastrophic. Now, obviously, there are good things and bad things about all of these. And the bad thing about this one is that if you've already built your town and you built it here, you're not going to knock it all down and rebuild it up here. That's not realistic. So it doesn't actually stop flooding at all, which is not useful, but it is incredibly cheap. And it does, again, if you manage it well, which we should be doing, but we are building on these areas because we're stupid. it will help you in the long run. Afforestation, that is the opposite to deforestation, planting trees. And you can see all these trees have been planted. Now, you can't see the trees have been planted because you can't see the trees. That's the nature of trees. Unfortunately, even the fastest growing tree takes 10 to 15, 20 years to establish itself. And in that time, you could still have a flood. So this is very much a long-term measure. But it does create nice habitats. It does look very nice. It looks very natural. You just have to make sure that the tree doesn't fall in and block rivers when we've got windy weather, for example. Again, have a look at these advantages and disadvantages. Could you extend them? Could you say this means that? Could you give an example? Dams and reservoirs, hard engineering. These are great, but they're incredibly expensive. I mean, we're talking billions. And because they're expensive and it floods all of this area behind in the reservoir, that's not something that's often chosen or very realistic in many places. But there are very big advantages. The Three Gorges Dam in China, for example, is the largest power station on the planet. It could power sort of between 5 and 10 Londons with the amount of energy that just that one power station produces. But several million people had to leave their homes, and many towns and villages were flooded as a result. Channelization is just the posh way of saying widening it, deepening it, and making your banks less likely to erode. So you can improve the efficiency of the river, or the river channel, I should say, without worrying about it moving or eroding or depositing. But it doesn't look particularly nice. It does also create a kind of Formula One track for the river, which means if you're fine if you live here, but if you live downstream, you're maybe not so fine, which is not so good. So again, be aware of those, have an idea of an example and how you could extend them. And then the very final part of this topic, which is the River Dee case study. This is just a way to get extra detail in, and you can see the path of the River Dee, the red line here, flows from Wales and out here, just up near Flint. So the formation, physical factors causing change and the human factors causing change, again, the same categories as Holderness. The River Dee source is near Dolt in Snowdonia, if I'm pronouncing that wrong, I'm sorry, which is down there, near Bala, which is much easier to say. There's very high rainfall, over 2,000 millimeters of rainfall a year fall there, which is often sort of good for the source, and it's a mountainous area. You can see from these brown areas that it's high. Okay, it's in the middle of Snowdonia. Now the Dee then flows east and northwards through the glaciated upland landscape of igneous and metamorphic rocks. So again, these rocks are very resistant. You get lots of waterfalls and things here. There's a place called Betsy Coyd there, that's not far. And again, I know there's a lovely river, waterfall there, but there's also many rivers and waterfalls that flow down the mountainside here too. Near Chester, the Dee meanders across a wide floodplain, eroding sedimentary rocks and depositing sediment. So there's Chester. So what you've got here is where it's in the lower course. This is the upper course, waterfalls, gorges, that sort of stuff. Middle course, you can see it's wavering and meandering a lot. And then this is sort of near the lower course where, again, you've got a wide floodplain, flatter land near Chester, which is the biggest city on here. Okay, this is the place that, other than Liverpool, which is up there, this is the biggest city on here, and it's grown up because it's nice and fertile land near the sea with the river nearby, obviously the Dee. The river then deposits at the mouth, forming the Wirral estuarine landscape. So up here, this is where you've got an estuary, so lots of sediment being deposited out to sea here. Now between Holt and Worthenbury, the landscape is floodplain, so between sort of this area here, it's floodplain, and there's lots of kind of lateral erosion causing the course to change quite a lot over time, but there's lots of alluvium as well, so this is very rich agricultural land. If the sea levels rose by 1 metre, then by 2100, quite a while away, the salt marsh, which is here near Flint, would be replaced by coastal areas, and this estuary would actually all be gone. So that's something that's causing it to change maybe in the future. So human factors that cause it to change, again, aside from all the different settlements you can see, between specifically 1732 and 1736, excuse me, they channelized 8 kilometers of the river itself. So they improved navigation, they increased the amount of discharge and velocity that went through it, so they managed it very well. And you can actually see on the map a section of artificially straightened human-made river here, just past Chester, again, just to help manage it and get it away from the settlements there out to sea. The River Dee regulation scheme, they actually built a lot of reservoirs, like the Llyn Celyn, which I don't know where that is, I'm sorry. and earth embankments were built along the middle course to protect agricultural land and property. So again, these are just ways that humans have changed the River Dee over the years. These are the physical things that have affected and changed the River Dee over the years, and this just shows you a bit of information about the River Dee. You will very unlikely to get a very big question on the River Dee. It just might help you with certain aspects to exemplify an example, to give an example from when you're talking about any of these factors that cause change. Okay, so that summarizes the longest topic, and you've bared with me for a very long time. The very final thing I will say just before I close this first topic off is there is a final section on here. It's question 4, glaciated upland landscapes. Do not answer this question. You do not get extra marks. You've not been taught any of the content specifically, so you are unlikely to get good marks, and the risk is the examiner will mark this, not one of your rivers or coast sections, and therefore you might end up losing marks at the end of it. So do not waste time by doing it. Just work your way through each page, make sure you don't miss out a section you're supposed to answer for the next part of the topic or the next part of the paper, but do not answer this question. It will be 12 marks just like the others are, with 4 marks and then an 8 marker. As soon as that 8 mark glaciated question is gone, which you've ignored, then your next section will start. Okay, thank you very much for bearing with me and listening, and the next topics obviously are going to be topic 2 for paper 1, and hopefully that will be a lot shorter for you and a lot more easy to digest. Thanks for listening.